Hi everybody, this is Mohammed Alshpool. I'm a PhD student at NC State University. In this presentation, I'm going to talk about our work simplifying persistent programming using battery-backed buffers. As you may have already noticed from the title, this is one of the works that investigates non-volatile memories. These are interesting devices due to their attractive features. They are faster than disk, denser than DRAM, and the fact that they are non-volatile means that we can use them to build a non-volatile main memory or persistent memory which can host data that would survive across crashes and reboots. However, these non-volatile memory technologies suffer from some important drawbacks. They are slower than DRAM, especially for write operations. They also have a limited write endurance, meaning that a cell in the non-volatile memory will wear out after being written to a specific amount of time, which is much shorter lifetime compared to DRAM. The third challenge we will talk about today, which is the one we will be focusing on throughout the rest of this presentation, is that utilizing the non-volatility feature we talked about in the previous slide introduces significant programming difficulties in order to maintain crash recoverability. To better understand these programming challenges, let us look at the following example. Here we have a simple system with two cores, each of which has its own private L1 cache, and both of them share the L2 cache. In our example, we have a hybrid memory system where we have volatile main memory, or DRAM, and persistent main memory, or non-volatile main memory. Each of the main memories has its own memory controller. For simplicity, we assume ADR in this system, where the updates become persistent when they reach the non-volatile main memory controller and even before arriving at the non-volatile memory itself. And in this example, we have two variables, x and y, representing two different cache blocks in the NVM domain, and both of them are initialized to 0. First, let us assume that core 1 will modify x to be equal 1. This update will be sent to its private L1 cache, and after getting all the coherence permissions and memory consistency requirements, it will be allocated and accepted at the L1 cache. At that point, we can consider this block to be visible to all the other cores in the same visibility domain, because any future access to this block will require requesting it from core 1 and therefore getting the most updated value. Therefore, we can imagine that there is a line at the L1 cache. We can call it the point of visibility, because any update that crosses this line and be accepted at the cache will become visible. Similarly, core 2 will update y to be equal to and allocate it at its own L1 cache after getting all the permissions and making it visible. So now we have both of the updates that are now visible. However, these updates are still volatile because they are in the volatile caches, and they will only become persistent or non-volatile when they are evicted from the last level cache and sent to the NVM. This can happen at unpredictable order due to natural cache eviction policies. Once any update is accepted at the non-volatile main memory controller, it can be considered persistent. Therefore, we can imagine a line at the non-volatile memory controller. We can call it the point of persistency, because any update that crosses this line will be considered persistent. Now let us assume here that y equal to got evicted and sent to the NVM first. So it became persistent while x equal 1 is still volatile. Then, if a crash happens at this point of time, we will lose all the content of the caches, including the update to x. Therefore, when we recover from the crash, we will have y equal 2 while x is still 0, which can result in an inconsistent state because the persistency ordering is conflicting with the visibility ordering. For example, it could have been the case that y was calculated as x plus 1, and thus having y to be equal to 2 while x is still 0 is not a valid state. However, we still see it because of this issue. This issue is known as the persistency ordering problem. And if you think about it, the main reason for this issue to happen is because we have a volatility gap between the point of visibility and the point of persistency, where the ordering of updates at these points can be conflicted. Several works have looked into this problem and tried to define some ordering rules or persistency models which controls the ordering of updates being sent to the non-volatile main memory. One of the most common approaches to guarantee persistency ordering is adding special instructions in the code, like writebacks and persist barriers, to define and enforce the persistency ordering. However, this approach is known to be very tedious and error-prone, as has been shown in several prior works. And there are several persistency models which differ in how strict or relaxed they are, but almost all of them share one important aspect, and that's they try to solve this persistency problem by facilitating the movement of updates from the point of visibility to the point of persistency. On the other hand, in this work, we look at this problem from the other way around. Instead of orchestrating the movement of updates from the point of visibility down to the point of persistency, we think of solving this problem by moving the point of persistency up to be at the same level at the point of visibility. Therefore, there will be no volatility gap because the point of visibility and the point of persistency are aligned, and any update that became visible will immediately and automatically becomes persistent without the need to add any special instructions. However, the question is, how can we achieve that and align the point of visibility and the point of persistency? There is actually a simple way of solving this issue. As we said earlier, the reason for this volatility gap between the point of visibility and the point of persistency is since we made the main memory becomes non-volatile while the caches are still volatile. Therefore, the most straightforward way to solve this issue is by extending the non-volatility implementation and create non-volatile caches in the same way we did for the main memory, by using some non-volatile memory technologies like PCM or STT-RAM. With this solution, the caches are now non-volatile, and therefore any update that is accepted at the caches and becomes visible will also be persistent at the same time. So we have eliminated the gap between the 2 points, and there is no need to use any special instructions for persistency. However, this might not be a very attractive solution, because using the same non-volatile memory technologies to implement the caches means that they will also suffer from the same non-volatile memory related drawbacks we talked about earlier. In fact, these drawbacks are going to be more significant in the caches because the number of writes to the caches is much higher than the writes to the main memory, which makes the write endurance issue worse, and the timing of the cache accesses has more impact to the overall performance, which makes the high latency issue of the NVM technologies become more pronounced. Therefore, implementing the caches using non-volatile memory technologies might not be the optimal solution. Another way of making the caches become non-volatile is by having a system with the battery-backed SRAM caches, so they will not have any NVM-related side effects. This solution enhances the ADR guarantees from draining the main memory controller content to also draining the content of the caches, and thus we call it EADR, or enhanced ADR. The battery will provide enough energy to drain the content of the caches to the non-volatile main memory in the event of crash, so they will not be lost. Therefore, effectively, the caches can now be considered non-volatile, which means that any update being allocated at the caches and becomes visible will also be persistent at the same time. And therefore, EADR will align the point of visibility and the point of persistency and provide all the benefits that we talked about earlier. Furthermore, EADR does not introduce any side effects on the system regarding the performance or the number of writes, because it only adds the battery to the system. Therefore, it can be considered to represent the optimal solution from performance and number of writes. However, for this to work and provide programming simplification, it needs to cover the entire cache hierarchy, which is expected to require a significant amount of energy and need to add a huge battery to the system. One of the main challenges with EADR is that the energy source or the battery need to be provisioned for the worst case scenario where all the content of the caches need to be drained to the non-volatile main memory. While in reality, a great portion of the cache content might not need to be drained because it might be updates going to the DRAM space, so it doesn't have persistency assumptions, or even blocks going to the non-volatile main memory space that are not dirty and thus does not need to be drained too. However, the energy source need to be considering the worst case scenario because failing to drain even one update to the non-volatile main memory might result in a correctness issue which cannot be tolerated. Because of that, we present our solution battery-backed buffers, or BBB. The main idea is to add a small persist buffer next to each L1 cache, which will be used to hold persistent updates going to the NVM domain at the same time they become visible. Similar to EADR, these buffers will be SRAM based, so they will not have any NVM related drawbacks, and they will be backed by an energy source like a battery to guarantee draining their content to the NVM when a crash happens. However, our solution requires a much smaller energy source compared to EADR. This is because our solution only needs to drain the buffers at the crash, and therefore it doesn't need to provision the energy source corresponding to the entire cache hierarchy as in EADR. And since any update allocated at the buffers will be considered persistent, our solution aligns the point of visibility and the point of persistency and provides all the programming simplification advantages as EADR, but for an extremely lower cost compared to EADR. One goal we had in our design is to try making as minimal changes to the underlying system as possible. Therefore, the updates held in the persist buffers are also kept in the caches to simplify coherence and improve performance when accessing this data. In addition, updates will be allowed to drain to the non-volatile memory during the normal execution time. And the energy source guarantees that even the few remaining updates at the persist buffer when the crash happens will also be sent to the non-volatile memory, which allows using smaller persist buffers while keeping the persistency advantages of considering the persist buffers to be part of the system's persistency domain. Now, after we talked about the design details, let us go back to our example and see how things will be different with our solution. As we said earlier, the main change is that our system has battery-backed persist buffers next to each L1 cache. So now, following the scenario we had before, once core 1 executes and allocates x equal 1 to its cache, it will also allocate it to the corresponding persist buffer when it becomes visible. And since any update allocated at the persist buffer will become persistent, therefore, the point of persistency in our system is at the same level at the point of visibility. Therefore, our solution successfully aligns the point of persistency and the point of visibility. Then, when core 2 allocates y equal to, it will also allocate it in the corresponding persist buffer at the same time it becomes visible. And therefore, it will become persistent. So let us now look at the case where y equal 2 is drained to the non-volatile memory before x equal 1, and if a crash happened at this point of time. So when the crash happens, we will lose all the content of the caches, but we will still have x equal 1 in the persist buffer because it's battery backed. And the crash will trigger the draining process, which will send x equal 1 to the non-volatile memory, and it will be there when we recover from a crash. Therefore, when we recover from the crash, we will find x equal 1 and y equal 2, which is the consistent state we are looking for, even though the update to x wasn't actually at the NVM when the crash happened. Therefore, as we see here, our solution aligns the point of visibility and the point of persistency and achieves all the programming benefits as EADR, but for a much lower cost. But to know how much lower cost our solution provides compared to EADR, let us look at some numbers. We focus on comparing the energy needed to perform the draining after the crash and the time it takes to perform the draining process, which will impact the turnaround time for the system after the crash. For our solution, the draining cost depends on the size of the persist buffers. The smaller the buffers, the lower the cost of draining. However, if the buffers are full, then they cannot accept any more persist requests, which can cause processor to stall and thus performance degradation. Therefore, there is a trade-off between the performance and the energy for draining, as shown in the table here. Therefore, it is important to choose the smallest yet large enough persist buffer size. In our evaluation over the workloads that we have investigated, we found that the best size is to be 32 entries per core. And since each entry has one cache block worth of data, this will be about 2 kilobyte data to be drained per core. And we have more details about choosing the best persist buffer size in the paper. For EADR, the draining cost depends on the cache hierarchy because this is the thing that needs to be drained when the crash happens. Because of that, we looked into two different extremes into the system when it comes to the cache size. One as a server class and the other as a mobile phone. And therefore, this will allow us to see how much our solution saves when it comes to the draining cost across these two systems. Furthermore, when we are reporting the draining cost for EADR, we assume that it will only drain the dirty blocks going to the non-volatile memory space. In our evaluation across the workloads that we looked into, we found that this will be about 44.9% of the cache's content. In this slide, we show the main results of comparing the draining cost when it comes to the draining energy as shown in the first table and the draining time as shown in the second table. In both of the tables, we look into the draining cost of EADR shown in the middle column and our solution with the default 32 entry size shown on the right column. And we look across the two system classes we talked about in the previous slide. The main thing we would like to emphasize in these tables is how much more expensive EADR is compared to our solution, as can be seen in the numbers highlighted in red in the tables. Our solution saves from about 300 times to 700 times in draining energy and draining time relative to EADR while providing the same programming advantages as EADR. However, we also want to show that these savings in draining costs didn't come with a degradation in the performance of the system due to the using of the buffers. To look into that, we now move to the simulated part of our evaluation, where we use GEM5 simulator to simulate the 8-core system with the configuration shown in the table, which will help us to compare the performance of both of the schemes. And we looked into multiple multi-threaded workloads as shown in the table here. In this slide, we would like to share the main simulated results that we have. On the figure to the left, we show the execution time on the y-axis corresponding to the workloads that we have looked in on the y-axis. The figure to the right shows the exact same thing, but for the number of writes to the NVM on the y-axis. On both of the figures, they are normalized to the base of EADR because it represents the optimal solution and from execution time and the number of writes, since it doesn't introduce any changes to the underlying system. As you see in the figures, our solution with the default size of 32 entries shown on black columns gives very close performance and number of writes to EADR. On average, our solution has only 1% execution time overhead compared to EADR and 4.9 overhead with the number of writes compared to EADR. Furthermore, these overheads can be gone even lower, up to about 0, if we extended the persist buffer size to about 1024 as shown on the dark gray columns. However, this will come with increasing the energy and the time needed for draining compared to our default size of 32. The final result we would like to share with you is to show the sensitivity study we did to come up with the 32 entries as our default size. On the y-axis, we show the workload's average overhead when we change the size of the entries from 1 to 1024 as shown on the x-axis, and all these numbers are normalized to the size of 1 in each group. The first group here, A, shows the number of times the processor had a persist request being rejected because the persist buffer was full. And this will be translated to execution time overhead as shown on the middle part here, B. Finally, the third part, C, shows the impact of changing the persist buffer size when it comes to the number of draining from the persist buffers to the non-volatile memory, because the larger the persist buffer, the more opportunities for coalescing that can happen at the buffers and not being translated to number of writes to the non-volatile memory. As you see across these figures, having 32 entries in the persist buffers shows the best trade-off. And after that, we start seeing diminishing returns when we increase the persist buffer size. And that's why we choose it as our default size. In conclusion, in this paper, we propose BBB, which relies on adding battery-backed persist buffers next to the L1 cache on each core. These buffers will be used to hold persistent updates and aligns the point of visibility and the point of persistency. With that, our solution provides the same programming simplification as EADR, but with much lower cost. We evaluate the best size for the persist buffer, and we use that size to conduct energy and time comparison with EADR. And we show that with 32 entries per core, our solution can provide performance comparable to EADR while requiring significantly lower draining cost compared to it. Thank you.